Problem 1.10. As you can see, I've already done this one, but let's go ahead and do it live. So let's just go ahead and grab a new page. And I might check my answer with what I got before just to make sure I'm on the right track here. Let's go ahead and do it again. Actually, I'm going to make that a little bit smaller because I'm going to go ahead and put this into landscape mode so that we can perhaps see a little bit better. Let's be a little bit more zoomed in here. And have some more Cabernet Sauvignon. Alright, so this problem, well, we spent pretty much most of section 1.4 of Griffiths was about normalization, and a lot was about the justification as to why it is that we can normalize a wave function at, say, time equals 0, and it can stay normalized for all time. So if the wave function is normalized at one time, I can normalize it for all times. And that's in my video about section 1.4 normalization. Now we're just gonna sort of like throw all of that on its head a little bit, because we're going to be talking about an unstable particle. So let's say it has some lifetime tau, and that means that now my probability of finding the particle is going to depend on if it's within its lifetime. So now my probability is a function of the time. So if I do my probability density here and I integrate it over all space, then that's going to equal some e to the negative t over tau. Now, one of the ways that we showed that the probability density, the integral of the probability density function over all space was not dependent on time, was to show that this integral, due to the Schrödinger equation, must be converging. So our solutions of the Schrödinger equation are limited to solutions that give a converging answer. We can't have our probability diverge over infinite space. So a big part of that in that equation, where we found that dp dt equals 0, was assuming that the potential energy was real. So now we are going to consider something else. We're going to consider our potential as having an imaginary part now. So now, instead of v being a real constant, I'm going to say it equals v naught plus I capital. Actually, I forgot what Greek letter that is. Capital thing. I think it's a gamma, but I'm probably wrong. I don't speak Greek or read it particularly, so no idea what letter that is. It's something though. So it is a positive real constant, but it constitutes the imaginary part of our potential. So for part A, we want to show that instead of the derivative of the probability with respect to time equal to 0, we want to show that it is in fact 2 times whatever letter that is over h bar times the probability. So To do that, we're first going to start pretty much where he started in Griffiths on this page. I'm just going to go ahead and pull up Griffiths so I can have it alongside me now. Once again, let's go ahead and make that guy smaller. And we're going to start here. So we know that the probability is going to equal, we'll actually just do that. That is going to be the same as d dt, and then the integral over all space dx of psi squared, absolute value psi squared, meaning that d dt p equals our integral over all space dx of the partial derivative with respect to time of our wave function squared. So I can move the full derivative outside the integral into a partial derivative inside the integral, and then we just use the product rule on this. So I now have complex conjugate d psi dt plus d psi complex conjugate dt psi. Now our Schrodinger equation tells us, so looking at this one right here, d psi dt is going to be I h bar over 2m, second derivative of the wave function with respect to space, minus I over h bar. And now we have, instead of just v as a constant, now we're going to have v naught plus I Greek letter and then psi. So this guy equals this whole thing. And then we have I h bar v naught psi, and then we have negative, plus is a negative, but I squared is another negative. Cool. So we got Greek letter over h bar times psi. And then for our complex conjugate, we have this, so we get a negative there, and complex conjugate, we get a plus here, and then that one would have been a plus. Oh yeah, it's just gonna work out the same sign. Okay, so here, making sure I got those signs right, we have a negative and we have a plus, negative and plus, positive and negative. Yeah, so we are good there. This part ends up being a real part because our i's ended up being squared. So we would have had negative here, or positive here, but negative here, and then negative I squared ends up being positive once again. Okay, now we're going to move on to our next step, which is just going to be putting that together. Here's where Griffiths got a little hand wavy, not bad though, but simplifying these two guys put together into this. So gonna actually go ahead and close that out so that we have a little bit more space here. So now we have this here, is going to be complex conjugate psi times I h bar. You know, I already know I'm going to regret not giving myself enough space, so let's go down even further so I have the full line. Alright, so d dt psi squared is going to be complex conjugate of psi, and then we have d psi dt over here, so that's I h bar over 2m d squared psi dx minus I over h bar I'm going to just parse it out completely. So then that's going to be times v naught psi plus that letter, whatever it is, times psi. And then that will be plus this guy, I h bar 2m complex conjugate and then plus that guy. I think we can already hopefully see pretty much where this is going. That if we had these guys once we simplify it down, right, before it's simplified to just having those constants being pulled out, and then our potential energy canceled out completely. But now, whereas most of our simplification is the same, we have this extra term in there that we have to account for. So to do this a little bit more explicitly, we already know what we're going to get in the end, but let's work it out to show it. So we are going to have psi complex conjugate I h bar over 2m d psi dx squared, so we have that guy, minus I'll keep it in order, there we go, complex conjugate of psi times I over h bar v naught psi plus whatever that Greek letter is. Oh, I said I was going to keep the same order and then I didn't. There we go. And then that will be plus minus all that guy, del psi complex conjugate, del psi squared, and then we have psi. And then that will be plus I h bar v naught psi complex conjugate, and then plus Greek letter over h bar psi star. Okay, now this term and this term are the same, so those cancel out. We have a negative sign, we have a positive sign, so that goes away. But this one is positive and this one is positive, so it did not go away. It stayed. Meaning that this guy equals, And now we have psi complex conjugate IH bar over 2m, second derivative of psi with respect to x, plus psi complex conjugate Greek letter over h bar times psi, minus all this junk, second derivative of complex conjugate with respect to x times psi, and then we have plus this guy again. So I know I've skipped a lot of steps in the past. I'm trying to be a little bit more explicit here. Hopefully I'm succeeding. So I'm going to pull out this constant. This is IH bar over 2m times psi complex conjugate, second derivative of psi with respect to x, minus, we already pulled out the constant, second derivative of complex conjugate of psi with respect to x times psi. And now we can just add these two guys together. For some reason, I like the aesthetics of this better. Probably because this equals this, which equals the probability density function. So that means that this guy equals this whole mess of a thing, which isn't that big of a mess, and then we're going to pull out a derivative of it later, just like we did for the normalization. And then we're going to have 2 times Greek letter over h bar times probability density. Alright. Now, if you haven't forgotten where we started, which you probably have, what we're trying to do is show that the time derivative of the probability function is going to equal negative 2 times gamma h bar p. So we have the time derivative of our probability function is going to equal integral over all space dx, this, because we just pull the total derivative with respect to time inside the integral and get that partial derivative. Now I can go ahead and replace it with this, although I suppose I should go ahead and pull out that x derivative. So let's go ahead and pull that one out right now before we stick it back in. And you can insert whatever dirty jokes you want there. It was certainly left wide open enough for it. And then we have this hanging out here. And then that's times p. Okay. So then I have the integral over x dx of this whole thing. Now, because I'm going to be adding another part to it, I realized my mistake right now. Let's go ahead and fix that. These are clearly not second derivatives anymore. Those are just going to be single derivatives. That was the whole purpose of that step, was to change those to single derivatives. There we go. Much better. That's a del. Make sure that's not a 2. And then my second integral, I'm just gonna pull these guys out because they're constant. And there we go. Well, I guess that wasn't quite P yet. Let's be better about this. Let's just keep it as psi squared. If we're going to be this explicit, let's be explicit in the right way, right? So that'll just be the integral of my probability density function, which is just psi squared, or absolute value psi squared. Now, what we showed in section 1.4 was that this integral all equals 0, and that's because the integral is just the antiderivative there. So what I have is psi complex conjugate, blah blah, all the stuff inside the parentheses that I just got from my product rule. And that's going to be evaluated at negative infinity and positive infinity. But my condition for the Schrödinger equation is that it converges. So it has to converge. So since it converges, if I evaluate it at infinity, it has to go to 0 because it's converging. If I evaluate it at negative infinity, it has to go to 0 because it has to be converging. So that means this whole thing is equal to 0, which is what we used before to say that if we normalize the wave function at any time, it stays normalized for any other time. And this is exactly the condition that we pulled to show that that was true. Now we're pulling the same thing, saying that this is all equal to 0, but we also have this other term out there. So we have d dp dt just equals 2 times Greek letter over h bar, this whole thing. And that is just the probability. So what I get is that dp dt just equals 2 Greek letter over h bar times p. Now I am missing a negative sign, and it probably came from here somewhere, is what I'm assuming. So I'm assuming it came from this, probably copy error. Oh, I guess I could just check my solution before. That would have been a better way to do it. Yeah, so there we go. Oh, no, wait, no, it is negative. But it was, yeah, I see where I made my mistake. That's what's nice about math solutions, is you can always find your mistake, and there it is right there. There's my typo. Right there. Should have been this. Oops. V equals V naught minus. There we are. Alright, so that's a minus, that's a minus, 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 and we did the whole solution with the wrong sign, but you know, it's easy enough to fix. Admittedly, it's easier to change negatives into positive than it is to turn positives into negatives, but you know, we can live with it. And then that's going to be negative, and then that's going to be negative, and this negative. There we are. And there we go. that is our solution to part A. It's very satisfying. So we found that if we assume that there's an imaginary part of the potential, that our time evolution of the probability is going to equal some constant factor times the probability. Now, part B says solve for PT and find the lifetime in terms of tau. So B, if we have lifetime is some tau, we want to find it and find this function of the probability. So if you're taking an undergraduate quantum mechanics class, I'm assuming you recognize this equation, that what we have is the time derivative of some function equals some constant times that function. So what this, if you're not familiar with the math, what this, and it seems like it might be circular reasoning, what this equation actually tells us a lot. So it tells us that the slope of this function with respect to time, there I go, putting the wrong axes on there. Clearly I have not been drinking enough to do this. Okay, so we have some function p, and that represents my y-axis. T is what it is dependent on. P is a function of t. So this tells me the slope of p, the derivative, equals the same function with another constant in front of it. So if I were to take the slope of this at any point t, then that slope would equal the same value as the function p with this constant out in front of it. So if I were to measure this at some t equals a, if I find the slope of it, it will equal the original function at point A times this factor. So we could work this one out just by, like, this is the beauty of Leibniz notation, that I could work this out and just say p, if I have the derivative of p equals this, then I can take the antiderivative of p. So I can take the antiderivative of this, and I can evaluate that. Or you can do it the way that, once you get past your first differential equations class, probably ordinary differential equations, if you're in ODDs now, then you're going to get familiar with this. The function that is its own slope is natural base, so that's going to be e. So p equals e, and then these constants out in front of it, 2 times Greek letter over h bar times t. If I take the derivative of that, then that's the derivative of the inside. So that's 2 Greek letter over h bar times derivative of the outside, which the derivative of natural base e is just e And then I could use substitution. I get the same thing back again. So, if you are new to this sort of math and you're taking quantum mechanics, you're going to be doing a lot more of it. Okay, so what we found is that our function, our probability function, probability density function, as a function of t equals exponential, and I actually should be a little bit more explicit here. I should make sure that I throw in some a, because to be fair, I actually have not normalized this function, so we could very well have a normalization constant a out in front. That will not show up in the differential equation explicitly because they would both have the same constant out in front. But we should put it in there to be fair. So that's our probability density function. We know that it was in this form, tau times t. Tau is like our characteristic lifetime. Anything that's inside an exponential has no units. So our characteristic lifetime is going to be something that has a unit of inverse seconds. So if time is in seconds, our characteristic lifetime is in inverse seconds. And that's going to be the point where, if I have time equal a specific point where my exponential is going to be equal to 1, or just natural base. So that's going to be where 1 equals to negative 2 times Greek letter over h bar and t. I solve that for t, and I'm going to get, let's say I want just negative 1, I'm going to get h bar over 2 over gamma. Or, I don't know if it's a gamma, to be fair. 2 h bar over 2 Greek letter. I said it'd be equal to negative 1, so I don't have to have negative times. I guess I don't like negative times. So that characteristic time is going to be h bar, or lifetime is going to be h bar over 2 times Greek letter. I forgot if Griffiths is okay with negative times or not. Oh, it didn't actually say what it was. In general, I like time to be positive, even though I know it's completely arbitrary. So our